Derivation of practical units from absolute units. From absolute units, the practical units are derived from the absolute units by either of two methods, each giving an identical result. The simplest method is to reduce the units of the absolute series to those of the practical series by multiplying by defined factors. The table gives the value of the units of the practical series in terms of the absolute units with the factors. The factors are all powers of 10 or multiples thereof. The practical units are defined as follows. Coulomb is 10 raised to the power of -1 in electromagnetic absolute units, and 3 multiplied by 10 raised to the power of 9 in electrostatic absolute units. Ampere is 10 raised to the power of -1 in electromagnetic absolute units, and 3 multiplied by 10 raised to the power of 9 in electrostatic absolute units. Farad is 10 raised to the power of -9 in electromagnetic absolute units, and 9 multiplied by 10 raised to the power of 11 in electrostatic absolute units. Volt is 10 raised to the power of 8 in electromagnetic absolute units, and 1 multiplied by 10 raised to the power of -2 in electrostatic absolute units. Ohm is 10 raised to the power of 9 in electromagnetic absolute units, and 1 divided by 9 multiplied by 10 raised to the power of -11 in electrostatic absolute units. The relations of absolute units are given as follows. 1 unit of quantity in electromagnetic absolute units is 3 multiplied by 10 raised to the power of 10. 1 electrostatic unit of quantity is 1/3 multiplied by 10 raised to the power of -10. 1 unit of current in electromagnetic absolute units is 3 multiplied by 10 raised to the power of 10. 1 electrostatic unit of current is 1/3 multiplied by 10 raised to the power of -10. 1 unit of capacity in electromagnetic absolute units is 9 multiplied by 10 raised to the power of 20. 1 electrostatic unit of capacity is 1/9 multiplied by 10 raised to the power of -20. 1 unit of potential in electromagnetic absolute units is 3 multiplied by 10 raised to the power of -10. 1 electrostatic unit of potential is 3 multiplied by 10 raised to the power of 10. 1 unit of resistance in electromagnetic absolute units is 1 multiplied by 10 raised to the power of -20. 1 electrostatic unit of resistance is 9 multiplied by 10 raised to the power of 20. There are slight mistakes in the way the table is read, but by looking at the data on screen, they are easily found. Example, calculate the equivalent of 5 volts in electrostatic units, absolute. Solution. A volt is equal to 10 raised to the power of 8 absolute electromagnetic units. Therefore, 5 volts are equal to 5 multiplied by 10 raised to the power of 8 absolute electromagnetic units. For the equivalent electrostatic units, this must be divided by 3 multiplied by 10 raised to the power of 10. 5 multiplied by 10 raised to the power of 8 divided by 3 multiplied by 10 raised to the power of 10 equals 5 divided by 3 multiplied by 10 raised to the power of -2, which equals 0.0166 electrostatic units. Alternatively, using the table, 5 multiplied by 10 raised to the power of -2 equals 0.0166 electrostatic units. Example, what is the value of 1 volt in absolute electrostatic units? Solution. From the above calculation, it follows that the value of 1 volt is 0.0166 divided by 5 equals 0.0033 electrostatic units. Alternatively, using the table, 1 multiplied by 1/3 divided by 10 raised to the power of -2 equals 0.0033 electrostatic units. Example, what is the value of 28.3 electrostatic absolute units in volts? Solution. As the electromagnetic unit is equal to the electrostatic unit divided by 3 multiplied by 10 raised to the power of 10, the reverse rule holds. The electrostatic unit is equal to the electromagnetic unit multiplied by 3 multiplied by 10 raised to the power of 10. 28.3 multiplied by 3 multiplied by 10 raised to the power of 10 equals 849 multiplied by 10 raised to the power of 9 absolute electromagnetic units. To reduce this to volts, divide by the equivalent of the volt in absolute electromagnetic units, which is 10 raised to the power of 8. 849 multiplied by 10 raised to the power of 9 divided by 10 raised to the power of 8 equals 8,490 volts. Alternatively, using the table, 28.3 multiplied by 3 multiplied by 10 raised to the power of 2 equals 8,490 volts. Example, an electromotive force of 120 volts produces a current of 5 amperes. Reduce these quantities to electrostatic absolute units. Apply Ohm's law to the result, obtaining the value of the resistance in the same system of units. Then, reduce the resistance thus calculated to ohms and test the correctness of the operation by Ohm's law applied directly. Solution. The absolute value of 120 volts in the electromagnetic system is 120 multiplied by 10 raised to the power of 8, which equals 12 multiplied by 10 raised to the power of 9. Applying the equivalent to obtain the value of this quantity in absolute electrostatic units gives 12 multiplied by 10 raised to the power of 9 divided by 3 multiplied by 10 raised to the power of 10 equals 4 multiplied by 10 raised to the power of -1 electrostatic units. 5 amperes are equal to 5 multiplied by 10 raised to the power of -1 absolute electromagnetic units. Applying the equivalent gives 5 multiplied by 10 raised to the power of -1 multiplied by 3 multiplied by 10 raised to the power of 10 equals 15 multiplied by 10 raised to the power of 9, which is the current in electrostatic units. Applying Ohm's law to the electrostatic units determined above gives 4 multiplied by 10 raised to the power of -1 divided by 15 multiplied by 10 raised to the power of 9 equals 266 multiplied by 10 raised to the power of -13, which is the resistance in electrostatic units. To test the correctness of the operation, proceed as follows. The original data gives the resistance by Ohm's law as 120 divided by 5, which equals 24 ohms. 24 ohms is equal to 24 multiplied by 10 raised to the power of 9 absolute electromagnetic units. Applying the equivalent gives 24 multiplied by 10 raised to the power of 9 divided by 9 multiplied by 10 raised to the power of 20 equals 266 multiplied by 10 raised to the power of 13, as found by the previous operation. This proves the correctness of the calculation. This example is given only as an exercise. The results are more easily obtained using the tables. The practical units of the electromagnetic system can be directly derived from the dimensional formulas of units by changing the units of length and mass. Let the unit of mass be 10 raised to the power of -3 grams, and the unit of length be 10 raised to the power of 9 centimeters, with the unit of time being the second, as in the absolute system. If these values are introduced into the electromagnetic dimensional formulas, the resulting units will correspond to the practical system: volts, amperes, ohms, and other regular engineering units. Calculate the value of the ampere in absolute electromagnetic units. An error crept in again, so starting from the previous paragraph again. Let the unit of mass be 10 raised to the power of -11 grams, and let the unit of length be 10 raised to the power of 9 centimeters, with the unit of time being the second, as in the absolute system. If these are introduced into the electromagnetic dimensional formulas of units, the resulting units will correspond to the practical system: volts, amperes, ohms, and other regular engineering units. Solution. The dimensions of the unit are mass to the 1/2 power, length to the 1/2 power, and time to the power of -1. Substituting for these symbols their values as given above, we have for the ampere 10 raised to the power of -11 over 2, multiplied by 10 raised to the power of 9 over 2, multiplied by time raised to the power of -1, equals 1 multiplied by 10 raised to the power of -1 CGS units. 10 amperes are equal to 1 absolute electromagnetic unit. Example, calculate the value of the ohm and volt as above. Solution. For the ohm, the dimensions are length multiplied by time raised to the power of -1. For the volt, the dimensions are mass raised to the 1/2 power, length raised to the 9 over 2 power, and time raised to the power of -2. For the ohm, 10 raised to the power of 9 multiplied by 1 raised to the power of -1 equals 10 raised to the power of 9 CGS units. For the volt, 10 raised to the power of -11 over 2 multiplied by 10 raised to the power of 27 over 2 multiplied by 1 raised to the power of negative 1 equals 10 raised to the power of 8 CGS units. The value of the reduction factor of the two systems of CGS units, which is also the numerical value of the velocity of light in centimeters, is approximately 3 multiplied by 10 raised to the power of 10. This value applies to the electromagnetic theory of light. The reduction factor has been determined with close approximation to the exact figure by several investigators with results that are reasonably concordant. The following are some of the results reached by recent observers. In 1883, J.J. Thomson found 2.963 multiplied by 10 raised to the power of 10. In 1889, Lord Kelvin 3.004 multiplied by 10 raised to the power of 10. In 1890, J.J. Thomson and G.F.C. Searle calculated 2.9955 multiplied by 10 raised to the power of 10. Later, Lodge and Glazebrook found 3.009 multiplied by 10 raised to the power of 10. Example. Calculate the dimensions of the reduction factor to reduce the electrostatic unit of capacity to the electromagnetic unit. Solution. The dimensions of the electrostatic unit are length. The dimensions of the electromagnetic unit are length raised to the power of negative 1 multiplied by time squared. To find the factor, divide the second by the first. Length raised to the power of negative 1 multiplied by time squared divided by length equals length raised to the power of negative 2 multiplied by time squared. This is the reciprocal of velocity squared. Example. Make the same calculation for current units. The dimensions of the electrostatic unit are mass multiplied by length multiplied by time raised to the power of negative 2. The dimensions of the electromagnetic unit are mass multiplied by length multiplied by time raised to the power of negative 1. Dividing the electromagnetic dimensions by the electrostatic dimensions gives mass multiplied by length multiplied by time raised to the power of negative 2 divided by mass multiplied by length multiplied by time raised to the power of negative 1 equals length multiplied by time raised to the power of negative 1, which are the dimensions of velocity. Dimensions of electromagnetic quantities. Two magnetic poles of equal strength and opposite polarity attract each other. This attraction is directly proportional to the square of the quantity of magnetism in one of the poles and inversely proportional to the square of the distance between them. Dimensions of magnetic quantity. Let the quantity of magnetism in each pole be represented by Q, and let the distance between the poles be L. The attraction between the poles is a force, and the dimensions of force are mass multiplied by length multiplied by time raised to the power of negative 2. For this specific case, force is proportional to Q text squared divided by L squared. Equating these expressions, we write the quantity of magnetism squared multiplied by the reciprocal of length squared equals mass multiplied by length multiplied by time raised to the power of negative 2. Solving for Q text squared, we find the quantity of magnetism squared equals mass multiplied by length raised to the power of 3 multiplied by time raised to the power of negative 2. Taking the square root, the dimensions of Q are mass raised to the power of 1/2, length raised to the power of 3/2, and time raised to the power of negative 1. Dimensions of current in the electromagnetic system. Let I represent the strength of a current passing through a conductor of length L. Assume the conductor is bent into the arc of a circle with radius L. Place a magnetic pole representing a quantity of magnetism Q at the center of the circle. The force between the current and the magnetic pole depends on 3 factors. 1. The strength of the current. 2. The length of the conductor. 3. The quantity of magnetism. The force is proportional to the product of the current strength, the length of the conductor, and the quantity of magnetism divided by the square of the distance between them. Substituting L for the distance, this simplifies to force is proportional to the current multiplied by the quantity of magnetism divided by the conductor length. The force also has the dimensions of mass multiplied by length multiplied by time raised to the power of negative 2. Equating the two expressions, we write Test current multiplied by the quantity of magnetism multiplied by the reciprocal of length equals mass multiplied by length multiplied by time raised to the power of -2. Substituting the dimensions of magnetic quantity, which are mass to the power of 1/2, length raised to the power of 3/2, and time raised to the power of -1, we find current. Current multiplied by mass to the power of 1/2, multiplied by length to the power of 1/2, multiplied by time raised to the power of -1, equals mass multiplied by length, multiplied by time raised to the power of -2. Finally, solving for current, the dimensions are mass raised to the power of 1/2, length raised to the power of 1/2, and time raised to the power of -1.